So lecture 19 is on derivatives and the definition of derivatives. This brings us to chapter 4, which I would say roughly speaking covers some statements and proofs of theorems that are commonly covered in Calculus 1. In fact, many of the proofs I'll share with you here I might actually do in Calculus 1 if I had a good class. So let's get started. The first thing is the notion of the derivative, right? So if we define this function phi of a, which is, what is this? This is the change in f over the change in x, where the change is based at a, right? I mean, essentially this is in the more sort of usual notation, change in x over change in y over change in x, right? Based at a. That would be the slope of the secant line connecting a and x, right? Anyway, that would be defined as long as x is not equal to a, right? So for, if the function is defined on an open subset of the reals, then we can consider the secant line from, a point in G to another point x, right? Anyway, let's see here. So since G is an open set and A is a limit point of G with A removed, thus it's possible to discuss the limit as x approaches A of phi A of x, which is this, right? And if that limit exists, then we say that the function is differentiable. We define that to be the derivative, in fact. So here it is. Okay, great. G is an open set. A is an element of that open set. We say f function f is differentiable at A if the limit of the difference quotient exists and is a real number. In this case, the derivative of f at A, denoted by f prime of A, is that value, whatever that is, right? F prime of A is equal to the limit of the difference quotient. And furthermore, if f is differentiable on G at every point A and G, then the new function f prime from G to R is called the derivative of f on G. And to be clear, that new function f prime of x is equal to, well, f prime of x. Well, that's not, it doesn't look like I'm saying it. Let's say it this way. So the new function is defined by x maps to f prime of x, right? For each x in G. Anyway, there is, of course, a distinction between defining the derivative at a point versus saying you can string all those values together to make a new function we call the derivative, right? So, but anyway, this is hopefully not a new discussion for you guys, but in any event. So there we go, derivative at a point and the derivative function. Now, here's an example. So I get my cover sheet here. So I should zoom in a bit. By the way, one thing I would say is this definition of derivative we just gave, right? It really only works in one dimension. You know that? Like this dividing by a number makes sense, right? If we had a vector for our domain instead, can you divide by a vector? Well, probably not. Except in the complex case, then that difference quotient definition still makes sense. And in fact, if you study complex analysis, you'll see the derivative of a complex differentiable function can again be given in terms of a difference quotient. But if you study differentiation in Rn over a more general class of algebras, you'll see that there's more to discuss there. But you can ask me more about that if you'd like to know. I know a little bit. Anyway, limit as x approaches a of f of x minus a over x minus a. In the case f of x is equal to x, well, that's just x minus a over x minus a. These cancel because, remember, the limit approaches a but not equal to a, and so we get 1. Of course, the derivative of the identity function is the number 1. In other words, the slope of the tangent line to f of x equals to x is 1 at each point. Because, in fact, the graph of f is its own tangent line in this case, but whatever. So, yeah, f prime of a is equal to 1. Now if we have f of x equal to x squared, we calculate the difference quotient, like so, right? And in fact, difference of squares, the x minus a cancels, we get 2a. Of course, you know the derivative of x squared is 2x, and in other words, f prime of a is 2a. And then finally, part C is a kind of a non-example. Although, so if they picked any other point than 0, right? The part C, I mean, yes, these arguments right here show you that the derivative at 0 does not exist because the right limit of the difference quotient is 1, whereas the left limit of the difference quotient is -1, and they're not equal, obviously. So the double-sided limit does not exist, and f is not differentiable at 0, right? But later in this section, I think, is it this section or the next one? I was looking at sections 4.1 and 4.2, so I may remember it from wrong, but eventually in this book, he defines left and right limits, left and right derivatives. And so like the left and the right derivatives at 0 exist, they're just not equal. Fine. But otherwise, right, if I looked at this, it's what? It's x for x less than or equal to, well, minus x for x less than or equal to 0. And it's x if x is greater than 0, right? You could throw equals in there if you want. But the point is, f prime of x would actually be -1 for x less than 0 and 1 for x greater than 0. So yes, the derivative here, the derivative here does not exist at 0, but it does exist everywhere else. So, you know, that's something. All right. Anyway. But it just takes one point to spoil it, right? So the function, absolute value function, f of x equals absolute value of x, is not a differentiable function because there is a point in its domain where it's not differentiable. It doesn't matter that every single other the infinity of other points other than 0, the derivative exists, and it's, well, -1 or 1. You know, that one point spoils the differentiability of this function, right? Now, if you change the domain and you omitted 0 from the domain, then, you know, if you define same formula, but f of f of the domain would be r with 0 removed. Then, if you change the domain like that, if you omit 0 from the domain, then that would still be differentiable. So it's it's very picky. Definition. All right, theorem. Let G be an open subset. Let me make sure I'm in frame here. Let G be an open subset. I tried to wipe off the lens here. It looks like it's less fuzzy. Let me try a little bit more. Maybe if I use this. I don't have any. Sadly, I couldn't find any lens gloss over the issue. Maybe this will work better. It's kind of the blind leading the blind. Let me just look a little bit better. I must have stuck my finger on there at some point or another. I don't remember doing that, but anyway. So here's the theorem. Let G be an open subset of the reals, and let f be defined on G. If f is differentiable at a point A and G, then f is continuous. In other words, differentiability at a point implies continuity at the point. All right. And so let's look at the proof here. Although it's kind of funny that he proves that here, like there's a lemma he gives later in this section. If you have that lemma, the proof is totally trivial, but whatever. The proof of this is more or less that lemma anyway, but whatever. So here's an identity. F of x is equal to f of x minus a plus a, f of a, right? And as long as x is not equal to a, we can also divide and multiply by x minus a, right? So we have this algebraic identity for the function. But we also know that in the limit as x approaches a, what happens? The limit as x approaches a, we don't actually consider x equals to a, right? So this identity holds in the limit. And in the limit, this quotient goes to the derivative, and well, that goes to 0, right? So in other words, the limit as x approaches a of f of x equals to the limit as x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a plus the limit as x approaches a of f of a. I can write that because all the limits I just wrote exist. This exists by assumption of differentiability. This is f prime of a, right? And this is a basic limit that goes to 0, right? And this is the constant, so that's just equal to 0 times the number plus f of a, which is just f of a. So we've just proved that, you know, the limit as x approaches a of f of x is equal to f of a. And since we have an open subset, we know that every point is a limit point, I believe. And consequently, the continuity is captured by saying the limit as x approaches a of f of x is equal to f of a. We've done that for an arbitrary point, therefore we've shown continuity. Well, I'm sorry, I don't have to do it for an arbitrary point, right? I just this theorem is for a point. So differentiability at that point implies continuity at that point. Great. By extension, if you had that the function was differentiable on its domain, of course it would be continuous on its domain as well, just applying this theorem pointwise, you know. Oh, there's my calculation, right? But I did a little bit more expanded version up there. Anyway, there you go. Remark: the converse of theorem 4.1.1 is not true. For instance, the absolute value function is continuous at 0, but it's not differentiable at 0, as we showed in the previous example. Fair enough. So differentiability is a stronger condition than continuity. All right. Like in a nutshell, differentiability says something about the existence of a tangent line, right? So like, whereas continuity just says that the points in the graph of the function are sort of glued together. They're adhering infinitesimally, one stuck to the next in some sense. Whereas differentiability says something about you can fit a line that is very, very, very close to the function, sufficiently close to a point, right? There exists this tangent line. Anyway, if we have a function, well, two functions, f and g, both are differentiable at a point, then the sum is differentiable, and its derivative is the sum of the derivatives, and a constant multiple of a function is differentiable, and its derivative is a constant multiple of the derivative. And what else can we say? Maybe a product rule? Yay, a product rule and a quotient rule. What do you know? So, man, we're about a month into Calc 1 now. Maybe we can pick up the pace a little bit. So, product of functions f times g, f g prime of a is, you know, f prime a g of a plus f of a g prime of a. This is the product rule, or sometimes called the Leibniz rule. And then, of course, we have the quotient rule down here, right? So how do you prove these? Well, direct attack from the definition will do it. There are other ways. If you look in my Calculus 1 notes that I wrote a while ago, I use the results of Cathedori and prove things in a slightly different way, but these are good proofs. It's fine. So the product rule, everybody does this. They start with the difference quotient, they add 0 in the middle, and then you break it into two fractions, one with f of x minus f of a over x minus a, which is going to give you the difference quotient for f times g of x, and over here we get the difference quotient for g of x times f of a. Now f of a is a constant, so we can just pull it out of the limit, and the limit of the difference quotient for g exists in g prime of a by assumption. Over here, the limit of x as x goes to a of g of x, well, we know that that's equal to g of a, because if g is differentiable, then it's continuous, right? So this is, by the previous result, we get that. And so, as he was saying, yep. And so, you take the limit, and he doesn't, they can't be bothered to write down the limit law that applies here. Fine, whatever. I could afford to see a little bit more detail in that proof. I think if you gave me that as the proof on your test, I think I'd probably take off a point. But anyway, I think it's fine. It's fine. I'm just saying they should take the limit of this and like, okay, fine, fine, fine. That is the main point, is that G is continuous, and everything else is kind of obvious. Fine, fine, fine. I'll get over it. Now, to show D, you just introduce a new function, h, equal to the quotient function, and then f is equal to h times g. So then f prime of a is equal to h prime of a g of a plus h of a g prime of a. And consequently, if you solve that for h prime of a, what do you get? You get h prime of a is equal to, well, f prime of a minus h of a g prime of a divided by g of a. But then if we multiply that by g of a over g of a, we get g of a f prime of a minus f of a g prime of a. Sorry if I'm off the screen. I'm sorry. Divided by g of a squared. Now, what's the problem with the argument I just scribbled here in the margin? The problem with this argument, I mean, that's the product rule, fair enough, but what do you need to do? What do you need to know for the product rule to hold? Well, you need to know that the derivative of that function exists, but knowing that the derivative of that function exists is not given here, right? We have the differentiability of f and g is given. We don't know that the derivative of the quotient is given, so this is not quite logical, is it? Although I'm pretty sure I've given that as a quote-unquote proof in Calculus 1, and as I recall, no student called me on it. Anyway, I'd say hindsight's 20/20, but then again, we've lived through 2020, and there's nothing much worth looking at in 2020, I think. Let's see here. I mean, anyway. So what's going on over here is we're looking at the difference quotient for h, and basically through this series of algebra steps we get that it's given by that, right? And then if you take the limit as x approaches a, well, this is g of a squared, this is g f prime, and this is minus f of a g prime. And so that calculation makes sense because you're only using limits and the existence of difference quotients limiting to derivatives as is given. This, on the other hand, assumes the point. It assumes that h prime of a exists, and we don't actually know that. That's the whole point of part D, you know? Anyway. But, you know, as I said, full confession, I think I'm guilty of giving this as a quote-unquote proof in Calculus 1 before. It might even be in my current notes. I need to fix that. Oh well. So here's an example. You can look at x squared as x times x, and so you can recover the, f prime of a equal to 2a from the product rule. And you can use induction to get the power rule for n by applying the product rule successively over and over. This is the lemma I was mentioning earlier. I think with this lemma in hand, the result that differentiable implies continuous is immediate. Of course, it's almost immediate anyway. So here it is. And I would say that this is awful close to Carathéodory, I think. Carathéodory. So if you solve this thing for u, if you solve this for u, what do you got? You got like u of x equals to, how's it go? Oh. What? Huh. Um, well, maybe it's a little bit different. Maybe not solve for u of x. Maybe I can see something better here if I mean, if we solve this for f of x, maybe it's kind of interesting. F of x equals to f of a plus f prime of a times x minus a plus u of x times x minus a. Okay, fine. So this essentially is, capturing the departure of f of x from tangent line at x equals to a, right? So the tangent line to x equals to a is exactly given by this formula right here. This is the tangent line. The graph of that's the tangent line. And so this extra bit, u of x times x minus a, is something that must go to 0 as x goes to a, because at the tangent line, the function and the graph and the tangent line should match up. So, anyway, I'll move on. So lemma, there exists this u of x from g to r, which satisfies the limit as x approaches a of u of x equal to 0. So here's the proof. He says just let u of x equal to the difference quotient minus the derivative for x not equal to a, and let it be 0 for a. The fact that the limit of u of x as x approaches a is 0 follows from the differentiability of the function, right? Limit of x approaches a of u of x is the limit of, and I like to put parentheses on limits like that. And so this part limits to f prime of a, and that's a constant, so it's just minus f prime of a. So there you go. Now once you have that in hand, it essentially gives you a formula. It gives you a formula to work with, and so it becomes easy to prove things like, in fact, you could go back. You, in fact, could go back and use this lemma above to prove, like, the product rule. Essentially, almost algebraically, you could prove the product rule. You wouldn't have to sort through difference quotients or anything. Here, I'll do it. Check it out. So, if you have f of x differentiable, then that means you can write it as f of a plus f prime of a times x minus a plus this kind of junk, u of x times x minus a. In fact, let me propose that instead of going through the trouble of calling it all that, let's just call it eta sub f of x, and notice that this eta sub f of x goes to 0 as x goes to a, right? And likewise, g of x we can write as g of a plus g prime of a times x minus a plus, well, v of x, let's say, times x minus a by the lemma. But I'm just going to point out we can call that eta sub g of x, and then notice that that goes to 0 as x goes to a, right? So, let me back it up here a bit. If you want to, then you can look at the product, f of x times g of x. And the derivative allows us to have this, I would say linearization, but it's really an affinization. It's the best linear plus a constant constant term. constant term here is f of a. The linear term is f prime of a times x minus a. So there you go, plus a to f. That's my f. My g is literally equal to g of a plus g prime of a times x minus a plus a to g of x, right? And so that is equal to f of a, g of a, plus f prime of a times g of a. F prime of a times g of a times x minus a, but then I'll also write plus f of a, g prime of a times x minus a. So I just collected together product of this times this and this times that to give me these terms. And then what's left? Well, plus like a to f of x times g of x plus, I mean this is all g of x, right? Plus a to plus f of x times a to g of x, right? But the thing is, you can then argue that, well, first of all, if you looked at this, you could see that this is really some function of x times x minus a, right? Tracking back. And you can identify this as the quote-unquote u of x for f of x times g of x. So what I'm actually proposing is that lemma, they've stated the lemma as, you know, if f is differentiable, then there exists this function. But you could reverse this as well, you know. If there exists a function u, which is continuous at a with limit 0, and satisfying this identity for all x and g, then that implies that f is differentiable at a, right? Because essentially the steps are reversible with that understanding. Let me think about that for just a second. If u is continuous and that identity holds, then we have the limit of this difference. Right, yeah, you could prove that the converse direction holds with what I just said, I believe. Anyway, so that if and only if statement, I think, is known as the, well, I think it goes back to Carathéodory. So what I'm trying to say is, I haven't quite given you all the details, but in that way of thinking, the fact that I can show that f of x times g of x is equal to this linearization, well, this affinization of these terms right here, and then there's this other piece which goes to 0 as x goes to a, shows you that what's underlined in green is in fact the derivative of the product. And of course that is exactly, I mean, what's underlined and what's boxed in red is the derivative of the product, because it's the coefficient appearing times x minus a. But anyway, I mean, take it or leave it. That's another way of thinking about it. You don't have to think about it that way if you don't want to. Just sharing something with you. So anyway, I'll get back to the chain rule now. So if we have f from g1 to r and g from g2 to r, and g1 and g2 are open sets with f of g1 a subset of g2, which means that this composition is defined, then the the derivative of the composite is given by the chain rule here, like the derivative of the outside function evaluated at the inside times the derivative of the inside function. And so you basically use the lemma. There exists this u of x with limit 0 that gives us this way of approximating f. Well, not approximating f, it gives us an identity for f that is related to the derivative. And likewise, since g is differentiable at f of a, there exists a function v such that, v of t goes to 0 as t goes to f of a, and we have g of t minus g of f of a is g prime of f of a plus v of t times that, right? But then if you let t equal to f of x, all right, then that gives us g of f of x. Sorry if I've gone off screen here. G of f of x minus g of f of a is, so again we're just plugging in, f of t, not dot words, I'm plugging in f of x for t, so there we go. And of course, as x goes to a, that gives us that u of x goes to 0, right? But also, as x goes to a, f of x goes to f of a because f is continuous. And if f of x goes to f of a, then v of f of x goes to v of f of a. In other words, the v goes to 0 by the composition of limits law. And so, and then he's just taken the difference, divided this by x minus a, you get the difference quotient of the composite. And again, as the limit, as x goes to a, we get that this piece goes to 0, and that u of x goes to 0, so we're just left with f prime of a times g prime of f of a, which of course is the chain rule. But I mean, this is lovely, but I think it also at danger of losing why the chain rule is true, and the real reason that the chain rule is true is just because the composite of lines has a slope formed by the product of the slopes. So because the derivative is essentially tied to the idea of replacing a function with a corresponding best approximating line, if you look at the best approximating line for a function and another one which is composed, you end up looking at the product of the slopes, which is the chain rule. So like, let me show you about this. F of x equals to, say, m1 of x plus b1. G of x equals m2 of x plus b2. If you compose f and g, f composed with g, I guess it was doing g composed with f for the other one, but whatever, then that's f of m2x plus b2, which then is m1 m2x plus b2 plus b1. In other words, it's m1 m2x plus m1 b2 plus b1. This is my point, is that this composite of two lines has the slope, which is the product of the lines composed. So the chain rule is actually very intuitive if we understand that the derivative is nothing but the best linear, well, it's the slope of the best linear approximation to a given function, provided it exists. Anyway, I'll go on. So here's an example of the chain rule, but I don't think I need to go through that with you. And of course we can apply the chain rule more than once, right? Like that. You get the chain of the chain rule. And great. And in fact, furthermore, we can extend our notion of differentiability to like second derivatives, right? If you can calculate the derivative, then you can say that the function is twice differentiable if the derivative itself is differentiable, and so forth. And we usually use like a f of 2 like that to denote the second derivative. So f prime prime is f prime prime, and likewise we can define the third derivative and so forth. In fact, we can define it iteratively, right? The n plus 1th derivative is the derivative of the nth derivative for n in the natural numbers. So he could have given a recursive definition for higher derivatives here if he wanted to. So the definition here assumes that the, it seems to be assuming that the derivative has the same domain as the original function, but in practice, as you differentiate, the domain of the first derivative may be smaller than the domain of the original function, and as you keep differentiating, you may lose more and more points. So like the domain of the 10th derivative of a function might be smaller than the domain of the function originally. However, oftentimes we want to assume that the derivative in the function and the whatever, the nth derivative of it has the same domain. And if we want that, then we say that it's n times differentiable function. In addition, we'll see that continuity of the derivative is even nicer. So a function which has a derivative which is itself continuous, then that's said to be a continuously differentiable function. So the derivative in principle can exist for a function everywhere, but that doesn't make it continuous everywhere, right? So we've talked about that some. I talked about that some in the other course. I gave an example of a function which was everywhere differentiable, but the derivative was not continuous at the origin because it oscillated really badly. But anyway, more about that later. Cni is the set of n times continuously differentiable functions on I. So that's it for this one. So thanks, guys.